thank you for joining our session. I will present you 3 techniques how to analyze a trace file where you're not exactly sure what to expect within the trace. So I've noticed there might be 2 major approaches to network analysis. So one objective might be we have a known server or a known application that is not behaving as expected. So we immediately know which IP address has to be analyzed. And the other situation seems to be more fuzzy, where users complain like, my cursor is blinking in an odd pattern, so that has to be a problem with the network. And so you're tasked with investigating like 1 million packets and find out where exactly is my problem. So if you've done that time and again, you will probably see a few things here that you've done by yourself. If this is the first time that you have to investigate a big trace file and you have to identify network errors or application errors in it, then this is a presentation for you. So thank you for joining, and here we go. We will work a bit through the OSI layers, working our ways from bottom up, which means before we start doing our network analysis, before we even break out Wireshark and start recording things and configure our span ports or put in the tabs, I highly recommend that you do a bit of investigation on the network or on the client side. So I've put here a screenshot from a show interface command issued to a Cisco switch. And usually the Cisco switch will not tell you the important information in red, but I've just highlighted it. So you can imagine that if your client is connecting in today's world at 10 megabit per second, well, you should ask yourself if that is the expected behavior, if someone has purposefully limited that speed to 10 megabit per second, or if something is wrong with the network card or something is wrong in the configuration. So if the user is expecting like a gigabit throughput because he's using on a big desktop publishing application or using some computer-aided design application, then probably 10 megabit per second is a performance problem, and you don't even have to take out Wireshark and record packets. You want to fix that first and then see if the complaint is still valid and it's still there. Now, when you record traffic, depending on your capture setup, you may record things at a choke point where you take in traffic from the inside and the outside interface of a firewall. Or you might have a choke point somewhere at a trunk interface with multiple VLANs going through. If you're investigating a scenario like that, I highly recommend that you take your trace file and split it apart into the individual virtual LANs, especially if you're not used to a complex investigation like that. So that you first go like, I have my VLAN 1, 2, 3, 4, 5, and I separate all of them into individual trace files. And the easiest way to check out if there are multiple VLANs present in a capture in the trace file is to use the T-Shark utility. So Sake Block has presented the use of T-Shark here in his last presentation. And this is usually, I stick to Wireshark as a GUI application, so with the graphical interface. But just to find out how many VLANs do I have, and to split them, these VLANs into individual trace files, that is where I use T-Shark. If you have just one trace file, T-Shark will do a good job in splitting all the virtual LANs into an individual trace file. Now, if you have like a collection of 1,000 trace files that were recorded over a full week, you might want to use the infamous Trace Wrangler utility, which does an excellent job of automating the whole process so that you will end up with a set of trace files in different directories depending on the interface properties or the VLAN used. So we assume that for the next couple of minutes that everything is in one file and you have just one VLAN to worry about. And we have no idea about the content, about the network. Probably they just bring you in as a consultant or as a specialist and go like, please help us to find out what is wrong in that network. You know nothing about their most important applications, about the IP addressing scheme used, and you might notice that the network topology that is there is like stamped with a ton of with coffee cups that left some marks on the network map. So you know that is might be a bit outdated and might be several years old. And then you should find a problem in that. Well, good luck with that. So the first thing that I do in a situation like that is I look at my trace file and I use the feature statistics protocol hierarchy. I personally find that a very helpful feature in Wireshark. Let me show you how that looks like. Actually, I could bring up a trace file here, which is like this. Here we go. Is that somewhat readable for you guys, or? So, as you see, we have everything here, which is Ethernet, great, not a big surprise. We have a few non-IP packets, like related to spanning tree protocol and some Cisco discovery protocol. And then we get some user datagram protocol, like just a very small number, like 1.5% of our packages are only UDP. And the majority of packets relate to TCP, and then it's probably a matter of, well, some HTTP and some SMTP. So with that in mind, we know that a few sort of exotic protocols are there. And if I analyze a situation like that, I tend to go like, well, that makes me curious. Why do I have like a few syslog messages in there? It's not like they're omnipresent here, but let's have a quick look. So it's just to please my personal curiosity. I have to know what's happening here. So I use this nice feature, right-click on the line where it says syslog now, and I go for prepare a filter, select it, and now note that Wireshark will give me here in my display filter line just the information like, hey, here's your syslog. And here we go. Now, isn't that nice? I get a message that tells me disk/dev/sda1 is full, error code, whatever. So great. So we all know it's not the network, but now we can prove it. And that's the first bone that we can toss whoever is in charge to ignore it and go like, guys, okay, here's something that you want to fix. So that is I just picked that protocol because it's just there. So I can tick that off and go like, okay, my syslog, I did that. So the next logical choice would be to go through all the protocols, especially like the quick ones, where I feel like maybe I find something or I know like, okay, I've checked it out and it will not reveal any problems. Do you see that? So here again, the screenshot for you guys. So once we did that, we want to work through the rest of the protocols, but it can be a bit distracting to go like, okay, now I did this, and now I go for HTTP, and then for SMTP, and maybe I sooner or later find relationship, like the query to a web server triggers an SQL query to in the backend, and to bring that together, it can be distracting. So personally, I prefer to stay in a more systematic approach, and that would be I follow all the OSI layers bottom up. So we already checked before capturing the physical layer. Remember that 10 megabit thing. So make sure the interface speeds are as you expected, the interfaces are error-free. Run the command netstat -E on a computer to see if some errors were recorded for that interface. And once you're set with that, and you took your trace file, let's go through all the layers and start at layer 2 here. So in this phase, I look especially at the protocols, spanning tree protocol, STP, or its variations like per spanning tree or MBSTP or whatever. We look at the broadcast domain itself, what we can learn from ARP or DHCP messages, and we look at layer 2 discovery protocols that are often found in a trace. Let's start with the spanning tree protocol. So what we need is a display filter that is called STP. And I expect that in my layer 2 topology, the whole network is always stable. So there's no change in the root bridge. It shouldn't be. As long as all the devices are running fine, there is the one root bridge chosen or configured by the network administrator, and that should be there. Your switches should not frequently be turned on and off. Still, that can use a ton of problems. Now, there are a couple of devices around that cost like 30 euros. Like Netgear, for example, has a wonderful 5-port switch that is powered by your USB port. It supports 5 Ethernet connections up to 1 gigabit, is fully manageable, supports multiple VLANs, span ports, and whatever you want to have. A great device. So if a user feels like, oh, I have to connect my buddy's computer here, or we have just added a network printer and I'm too lazy to demand a proper port, let's connect everything to that 5-port switch. And because I'm too lazy to run a power cable, I use the USB-powered connection. Now your new port switch comes in, takes over the role as a root bridge, and the user folds down the computer because he walks away into a meeting. Suddenly your root bridge is unpowered and you have a change in your topology and everything seems to stop for a couple of seconds or maybe a minute. So, of course, you can protect your network against that. You can configure your interfaces that your switch will not accept these STP packages. Yes, you can do that and you should do that. But then again, you probably did not start the whole investigation if everything was configured in a perfect way. So make sure that your network topology is free of any changes. Now we're looking at the spanning tree protocol, and the easy things are, you know the MAC address of your root bridge. So you type in something like this, not STP and not stp.root.hardware address. Or you could focus on the topology change flag. That is one flag set in every spanning tree message. Let me show that to you on the in the trace file. I have to change my configuration a bit. You will notice that Wireshark in the default configuration will use that light gray color, so it's not distracting your eye with these layer 2 messages. I turn off my coloring here so that it is easier for you guys to read. And note that here in the column, what you see in the info column, that the root bridge is the same for all these packets, which is exactly what we want to see. Also note that we have one field called flags, and here's a thing called the topology change flag, and that flag should be at 0 at all times. That indicates that your spanning tree is just stable and is not aware of any changes. If something odd happens, if someone is changing the network, you might experience a view like this. That's a trace file that I took from Johannes Weber's website, where you notice that the topology change flag is set for a short period of time, and a new bridge is coming in, a new root bridge is coming in, so probably a new switch was powered on, and notice that the cost has changed. So from cost 0, we can suddenly go to cost 4. We see a new MAC address is coming in as source MAC address, and after 2 or 3 frames being exchanged, everything goes back to normal. So it tells me, well, something has happened in the network on the layer 2, but we have to find out if that was on purpose or if something more weird has happened. The next protocol that I like to look at is the ARP protocol. And you probably know that the ARP protocol is used to translate IP version 4 addresses within your broadcast domain to a MAC address that will be used for frame forwarding. And so when I look at use the function statistics endpoint and then Ethernet, I can see the number of layer 2 hosts visible in that broadcast domain. Sometimes we find really big broadcast domains with like 10,000 hosts in it. Now, given the fact that we have like the Bonjour protocol from Apple or multicast name resolution on Microsoft systems and any other broadcast protocol, this can create quite some noise in the background and block the network for a certain time. So make sure that you don't have too many systems in your broadcast domain, or if it is within whatever your network designer has found correct for you. When we look at ARP packets, we might see something really, really odd. Like, what do we have here? What can you guys find on here? If you look at that, you've been using Wireshark for some time now. What can you see here? Just shout it out. What can you see in terms of strange things that jump at you? Wrong subnet mask. Correct. So just in the first frame, we see that probably that system is using a wrong subnet mask. So by the address, we can guess that it is probably a Class C network with a subnet mask of 255, 255, 255.0. Well, or whatever should be correct for that network, but it would be very strange if we have just a subnet mask covering the first 2 bytes of the IP address. There's another rather odd feature here. There's a different MAC address. It seems to have also a wrong subnet mask. We see that we have 172.29 as the first 2 bytes in the IP address, and it's asking for a MAC address of 172.30. But it's also asking for different MAC addresses, like in the 192.168 area, which is completely off. So there's rather no common bit in there. So that is a very odd behavior. Has any of you ever encountered a situation like that? Actually, I find that odd. And there's only one situation and configuration that I'm aware of, that if you have a router that points a default route to an interface and not to an IP address. So if you have a router that goes like, my default route goes out interface Ethernet 00, and then we'll ARP for the remote IP address and hope that someone is using proxy ARP to pick that up. So either you're using this rather unusual network configuration where you just dump things on an interface and hope someone is picking it up, or maybe somehow you're lacking a default gateway for that device. At least I would check out the configuration of that computer here, 172.29 something. Once we've checked all these ARP packets, actually ARP packets are nice because you would only find a few of these ARP packets in your network. So compared to the big traffic of like the real user data, like IP or IP version 6 traffic that is happening and transport the real data. So that is very easy to check. You can quickly tick that off your list. Remember the list of statistics protocol hierarchy. And the last part that I check in this phase is a layer 2 discovery protocol. And that could be either CDP or LLDP, the link layer discovery protocol. And I might learn something about the IP addresses of devices, maybe about the software version that is used. And because the switches and routers always run their own software, it might be that we find a buggy or outdated software. Now look at that. Here's a Cisco discovery protocol that will nicely tell you when that operating system was compiled and published by Cisco. And you will find similar messages from other vendors as well. So I have to ask myself, hey, that is some iOS dating back to 2004. Is that device even still supported? And if someone goes like, no, we don't have money to replace network equipment, we just live with what we have, and we use the equipment until it breaks, great, that's your decision to make it, but please be aware there might be bugs in that system that somehow behave strangely, oddly, and influence your whole network, and it's not behaving as you would expect it to be. So now we've checked the layer 2 thing, and we've covered protocols like SDP, ARP, and the discovery protocols CTP, LLTP. So it's time, once we found that our network is stable and we're happy with the configuration that we found, we move to the next layer, which would be layer 3. Like now looking at IP addresses, at routing, and things like maybe name resolution. So first of all, many systems today use the DHCP protocol to obtain an IP address. If the DHCP process fails for whatever reason, the nodes revert to a dedicated network segment using the addresses 169.254.something. This network segment is called an APIPA address, an automatic private IP address. And if I look at a network trace, I never ever want to see a source IP address of 162.254, because that tells me right away DHCP has failed for whatever reason. So either you fix your DHCP server, or you assign a static IP address, or you shut down the interface at all, because you won't have any successful communication, any successful, reliable, predictable communication with that type of IP address. If DHCP fails, odd things happen in your network. So let's look at that. Who of you took the class at the beginning of the conference? Nobody? Just a few? Okay. I'm pretty sure you talked about DHCP, is that correct? I shouldn't have put all that in, but what is the point that allows me to draw a line to connect all the DHCP operations belonging to one computer? It should be the transaction ID, because a computer would always send out that DHCP DORA, discover, offer, request, acknowledge. These are the 4 phases for the DHCP protocol. And we see here a pattern where we have the discover and offer, where the workstation is asking for an IP address. The DHCP server goes like, hey, I have an address for you, this is my offer, and for whatever reason, the DHCP client does not like the offer. It doesn't want it, and goes like, well, I try again. And notice that we have a transaction ID here, and that address, that transaction ID 8033000, that is always coming from one system. Actually, with an IP address of 000, it's a bit difficult to spot the connection. So the next nice thing is we add a new column to our Wireshark window, and we look at the source MAC address. And now we can clearly see that there are 2 devices out there that have a problem obtaining an IP address. Now, what are the chances that 2 or more end systems share the same problem? Or do we maybe have a problem in our DHCP server, or somewhere a DHCP relay server sitting in the middle? So you want to analyze, probably in a situation like that, you might want to investigate the server side first, because you have multiple clients sharing the same symptom, they don't get an IP address. And after a certain time, the DHCP client will give up or just assign itself one of these 169.254 addresses. So once we made sure that all the DHCP is correct and we don't have APIPA addresses, it's a good opportunity to look at the topology not from a layer 2 standpoint, like with all our spanning tree, but from a routing span standpoint. Now, I don't know what routing protocol you're using in your organization. Maybe you're using multiple routing protocols, but usually it's one of the protocols that is shown here on the slide. It might be OSPF, RIP, or EIGRP, ISIS, and none of these protocols should indicate a change in your topology. With RIP, it requires a bit more work because you have to look at each message to see if something has changed, if like the hop count has changed for a certain network. But for OSPF, for example, that's pretty easy to spot because as soon as the network topology changes, you will notice that there is a link state update transmitted by the designated router on your network. So you don't want to have these link state updates, except it's like a frequent, a regular retransmission of the whole link state database. And the worst case that I've seen covered something like 70,000 link state updates in one day. So 70,000 link data. Every time a router receives a link state update, it has to recalculate the whole topology for that whole OSPF area. So that causes a lot of stress on the CPU in the router, and in the end caused the router to drop a few packets that were meant to be forwarded, which was not so good, to say the least. It turned out that it was like a misconfigured load balancer somewhere that injected at random times /32-bit node routes into the network. So you want to avoid these link state updates because that indicates somewhere a link is broken or comes up and down or something else is happening. So make sure that nothing happens like that. Now, most network operators or network engineers that I talk to go like, oh, I never look at OSPF because I see the topology changes on the console of my router, or I'm forwarding all that to my central network management system, and it will alert me if there's a change in the network topology. Great. If you have a system like that in place, well, then you hopefully somebody has already noticed that, picked up on the network change, and fixed probably the line. But then again, there's a reason why you were called out to bring in your Wireshark and all your expertise and go like, well, I have to analyze every single packet to see if something is wrong. So, and still, if you find a ton of these link state updates or other changes in your topology, go to the network administrator, ask him to fix it. The next set of protocol that I like to look at is the ICMP protocol. ICMP is often used as a base for the ping command, and I guess we've all pinged one or two servers in our professional career, and we're like, okay, so we know the regular ping can be ignored. Now, if you have a network trace in that statistics diagram, and you notice like, well, 90% of packets here are ICMP, you want to go for ICMP right away because that's not normal, full stop. But in general, it's a nice idea just to examine all the ICMP packets, and you can ignore all these echo request and echo reply packets, and you do that by using the network or the display filter that I've provided here. So you eliminate the code 8 and code 0 parts, and that leaves you with all the interesting packets. And especially you could find things like, communication is administratively prohibited, or port unreachable. So that would be interesting packets that indicate a problem or that you might want to follow up on. That more or less concludes the IP layer. So we check if IP addressing is correct, if the routing is correct, and we check some odd ICMP packages that should not be in the network. By the way, if you guys have any questions, just jump in. So the next part to investigate would be the transport layer. And the transport layer, that would be TCP or UDP. And I would like to focus here on a few things that relate to TCP. Usually on SharkFest, we have a lot of excellent presentations that cover just individual topics like what is the proper window size or what is the retransmission behavior of certain stacks. So I don't want to dive as deep as whoever is giving the presentation like this, but I want to give you just some basic troubleshooting ideas on things that can quickly be checked in your analysis project. And the first thing is that I expect that every single SYN packet gets answered with a SYN-ACK. And that means, like, I have that three-way handshake that starts every TCP communication, that the client goes like, hey, dear web server, I need a response on port 80, or dear mail server, I need something on port 25, or whatever your application requests. And these requests should be satisfied by the server. They should not go unanswered. They should not be rejected by the service, because that could mean like, hey, there is currently no web service present on that IP address, and that might be a problem. So in this slide, you see two different things. So the first part is the successful three-way handshake. Notice that we have the flag SYN initiated by the client that opens up the connection and goes like, hey, I want something from you. The server responds with SYN-ACK, yes, I'm ready. And the third packet with just the ACK, that would be the third part of the three-way handshake, and now the two can start to exchange data. If things go wrong, usually you would get a reset packet that goes back. Like the server goes like, hey, I want something on port 443 for my HTTPS service here. And the server goes like, sorry, no SSL server available here, and sends a reset back. So you don't want to see that second part, that second half in your trace file. And here's a display filter to identify these packets. So make sure that you use the relative sequence numbers in your TCP, and then you go like, the TCP reset flag is set, which is the RST that we've seen in the last slide. And then the sequence number is depending on your IP implementation. It could be like 0 or 1, but small or less 1 usually gives you like an idea, well, here we go, yeah, that is like a reset that is just referring to my SYN packet. If you have a larger sequence number, it could be that someone has just disrupted the connection and went like, okay, we've exchanged all the information that we have through, we drop this, thank you, goodbye, and they just sent the reset. Another important part in the TCP protocol is the window size. The window size indicates to the remote system, hey, you can send me X byte of data. So investigating the window size, determining the correct and optimum window size for a full-speed data exchange between two sites depends on the maximum bandwidth available and on the round-trip time between two systems. But be aware that any server or any receiver can inform the remote side like, dude, I cannot take any more data. Whatever you have sent to me, I have to process the data before I can accept more data from you. I will show you how that looks like in a second. So that is like, my receive buffer is currently full, don't send more data. That is a symptom that is pretty easy to spot within a trace file once you know what to look for. So actually, for that investigation, we hopefully have captured the three-way handshake, because there's one important parameter that is exchanged as part of the three-way handshake, which is called the window scaling factor. That tells us that the window size as specified in the TCP header probably has to be multiplied with a certain number, and that number is given in the initial handshake together with the SYN flag, and that is called the window scale factor. Now, here's a display filter that helps us to locate problems within that receive window. So we go like, it could be less than 1,000 byte. Pick any small number that it could be 1,400, which I would consider even still a very small number. Maybe it's even going down to 0, so you know something is wrong. And the scale factor -1 is used by Wireshark to indicate, sorry, I don't know the scale factor, I have not observed the three-way handshake for that connection. So we cannot really, we don't know if that number that we see, if that is like meter per second or kilometer per hour, so we don't know which unit to apply to. So we ignore that if we cannot just tell how useful the number is in terms of a performance analysis, unless we have the three-way handshake. And also, for if a connection is aborted using the reset flag, usually the sender will indicate a 0-byte window, going like, don't bother sending me any data because I'm closing down that connection. So with these flags being said, we quickly find problems here. And I've used coloring rules provided by Jasper Bongartz to highlight the potential interesting flags, like here TCP problems. And these packets, which are here shown in red, are marked by Wireshark as bad TCP. Let me show you how that works in TCP. That's a very helpful feature. Ooh. Let us go away. We have the coloring rules within Wireshark. It's like view coloring rules. That brings up this nice dialog window. And here's a filter that you should find, which is called bad TCP. Usually, these packets would be shown with a black background and red foreground. That is a bit hard to read here on a projector. So I've changed that to highlight it so it's a white background and hopefully easily spotted. And notice that the filter is like TCP analysis.flag, and it's not a window update. That is the display filter used to describe the packets which should be shown with the red letters. Oops, TCP. Here we go. Once I have selected all the the proper color set, I tend to scroll through the whole trace file using the page down just to spot odd things. I go like, oh, hang on, here's something that should not be there. Like here's that red line, a duplicate acknowledgement that indicates like maybe we've lost the packet somewhere. So and voila, a retransmission. In this particular trace file, you will notice that we have here a 2-second window. Look at the time here. We have a time of 000, and then it's 200 milliseconds, and then there's a 2.5-second delay between these two messages, which is certainly noticeable by the users. If I wait 2 seconds, you will wonder if I'm still there, and that might cause some stress. So that is something that has to be investigated. Now, Wireshark has a wonderful feature which is called an expert, and if you go for Wireshark, and is that correct? Okay. We have down here, notice in the lower left-hand corner, we have that red or yellow button that indicates like the severity that the expert has found within all the packets. We see here that something is in red and yellow, and it should be like a chat message which goes like, okay, just to let you know, we have like a certain HTTP request, or it could be something wrong. So that's an overview of all the messages that Wireshark finds strange here in the trace file. And notice like, oh, this here is an excellent number, isn't it? Like we have 11,196 connection resets, so that is something to investigate. Who of you is still with me? Who could tell me how can I find all these resets? Big thing, right click, apply as filter selected. Somewhere click in that dialog window, and here we are. And we see indeed, yes, we have like a ton of reset packets here. And We probably want to find out if that is correct, if there's some service not properly connected, and we have to check if all the sequence numbers are correct. Nope. Oh my. No, I messed up. Excuse me. The next interesting part is a round trip time. So if you are calculating round trip times within your network, I would expect that you have something like a millisecond or maybe less within your building. If you stay within a city, it should be just a few milliseconds. And if you have a wide area link that covers like half a continent or goes even further, it can be several hundred milliseconds, depending literally on the length of the cable. So if a round trip time that you observe is like a long round trip time or a short round trip time, really depends on your network architecture. Like how far is the remote system away? If I ping, say, a server within a riverbed that is sitting somewhere in California, I would expect a round trip time of 200 milliseconds easily because I have to go halfway around the globe and come back. If I want to ping a system that is sitting somewhere here within Portugal, I can imagine that I get a response time or a round trip time of just a few milliseconds. So if you see a round trip time of like 10 milliseconds within a building, you should check where that delay is coming from. So let's see how we can calculate the round trip time. So first of all, we need a TCP connection with a proper three-way handshake. And we have here, just by chance, a proper three-way handshake on that screenshot. And notice the first packet, which is number 3141, where the SYN packet is sent. There are two extra flags which are ignored here, and they are not helpful for this investigation, but still, I use that packet and set this as a time reference. So I select this packet, press Ctrl-T to use it as a time reference, or I use right-click, set as time reference in Wireshark. And from then on, every second in the time column would show me the time in reference to that frame. So we see that after 15 milliseconds, we get the SYNAC frame. So again, notice the three-way handshake with the first three packets, like the SYN, the SYNAC, and then in 3143, the last part that completes the handshake. And I look at the third packet from the three-way handshake, and because I've set that Ctrl-T as a time reference, I now can read my three-way, the round-trip time here from the third packet. And that method will work no matter where you have captured your data. So you might notice that this trace was taken close to the client because it takes us 15 milliseconds to get the response in the SYNAC, and we see 0 milliseconds from the SYNAC to the ACK. If I had observed the same trace on the server side, I might have seen a time difference of 0 milliseconds between SYN and SYNAC, but 15 milliseconds between the second and third packet. So I always look at the third one, and I see, at this time, it's 15 milliseconds. Here we go. Now, again, if that is a slow network or a fast network, depends on your individual topology. And if these are like in the same data center, you probably want to check out what device is causing that delay. It could be like a load balancer or a firewall or something else in there, some active component, or maybe just the server itself is so much under load that it will not respond in a timely manner. If you look at the expert diagnosis delivered by Wireshark, you might notice retransmissions. Now, retransmission, that sounds like, oh my God, we have lost the packet, and now we have big problems here, and everything is slow. But don't worry if you have a single retransmission that literally will be usually covered by TCP, and you will hardly notice that a packet was retransmitted. But yeah, if you have a ton of retransmissions, then you want to investigate the link and find out where did we lose these packets and why did it happen. Like, do we have a faulty line somewhere, or is something else wrong with the network? So just a single retransmission is not bad, but if you have a lot of retransmissions, especially if they focus on one server, on one subnet, you want to investigate that and see if there's like a device or a cable that has to be corrected. And the last part that I found really, really helpful in Wireshark are all the application protocols that support the value .time. Notice that I've just selected 3 of these protocols here, like DNS.time, SMB or SMB2.time, and HTTP.time. And there are many more protocols where Wireshark will show the response time. And now it depends on your configuration and on your individual topology if a DNS server, say, would respond within 100 milliseconds or within 5 milliseconds. And all depends on what queries you're using, how is your network configured, how are your servers configured. But take your time to find out which services should answer in what time. It's like my DNS server usually answers within 50 milliseconds. Okay, great. Suddenly it uses 200 milliseconds. That's a lot longer than usual. And you can search for these values by typing Control F for the find feature in Wireshark and enter like DNS.time is greater than whatever your baseline gives you. So it is very helpful to have a baseline of your service response times. And so you know, oh, okay, now everybody is complaining it's slow, and that is because the file server is slow today, or because my DNS server is slow. So this I find is a big help if you have a baseline and you know the usual response times for your applications. Now, once we have prepared all our, or done our analysis, we are challenged with presenting our findings to probably non-technical staff. So maybe they go like, well, we have suffered so much from that network outage or from these performance problems. Now you go to the boss and describe to them what has happened. From experience, I know that it is very easy to get kicked out of the boss's room by going to him, hey, yeah, you see, we had that window scaling option probably misinterpreted by some server, and therefore it was like 2 raised to the power of 8 and multiplied by something. I promise you, you will lose him within the fraction of a second. So that is like you get a reset and go, like, thank you very much, goodbye, goodbye. Usually it helps if you present certain issues, like here, what types of protocols do you have? And we have that great feature in Wireshark where you can use the I/O graph to show, well, how many bits per second or packets per second are related to an IP address or to or a protocol. Basically, you describe the interesting packets by using a display filter. Now, for starters, I go like, well, I'm interested in packets relating to mail, SMTP. So I use TCP port equals 25. So here we go. Look at all the packets related to SMTP. Now, that's a nice feature, by the way. That is a sneak preview. There's a first time for everything. Usually, I only install the most stable build of Wireshark. Now, that's taken from the development build, and Roland Knall was kind enough to add a new feature just for this presentation here, which is excellent. So once I've focused on a certain protocol and I find certain interesting packets, I use statistics, I/O graph, and note that my Wireshark, it's now shown in packets per second. I switch this to bits per second. And maybe I use here a line as well. I use a different color, like red. And I dare say that we have a certain correlation between all these lines here and the SMTP traffic described here in red. I can fiddle around a bit, and I could use here a feature like an impulse. And now I see the line like these impulses. And there might be a different interesting protocol which I've figured out a bit earlier, and I type in the display filter to describe another interesting part, which is, I think, this one. Port 3128, and I screwed up. Sorry for that. (3128), where is it? Use that in green, and we don't use packets, but we use bit per seconds. And now, well, that is not nice, isn't it? We notice that here there's a certain base traffic, like which seems to be like related to port 3128, and the rest is up there. So might be better to change this to a line, and this one to the bar, and we can play around until we have like a graph that we feel like, okay, this is something that is understood by manager, and they go like, oh, okay, now I notice that the green part here, that is like my proxy server that is taking a certain set of traffic, and the other half in the second part of the trace file is probably mail related. So I find this a very, very powerful feature in Wireshark to visualize certain results, especially if it deals with a burst of traffic causes interruptions in a different section of the network. Yes, please. Yes, actually the new feature is, which will probably release with the next production release, or if you download the latest development build, it takes the display filter and highlights all packets matching the display filter in your graphics. Probably something else will change. You will notice that on the left side, the label for the y-axis is like in an engineering format that goes like, it's 2 times 10 to the power of 6 bit per second. Well, I'm not that much of an engineer to keep that in the back of my mind and translate to kilobit or megabit per second. So I hope that they will change that soon into something like kilobit or megabit per second, which I find easier to translate into bandwidth than just these powers of 10. So there are many ways to play around with that, and I encourage you to highlight interesting traffic using these display filters. I know that this is like a lot that I've just dumped on you, and especially I couldn't give you chances just to run the exercise by yourself. So we will soon publish a series of blog entries on the blog of Packetfoo. So if you want to take down the node or follow us on Twitter, Jasper and me will publish articles where we redescribe all that in writing and give you a chance just like to expand your collection of display filters so that you can hopefully apply everything that we've covered and the challenges that lie ahead of you in terms of network analysis. So thank you very much for staying with me so long. I hope you found that interesting.